Okay, we're going to continue chapter 5, section 1. This is going to be on solving exponential equations using the one-to-one property. And at the end, we'll do some money problems involving compound interest. Okay, so the one-to-one property of exponents just states that if you have two exponential expressions with the same base, then the exponents also have to be the same. So basically, a to the power of x equals a to the power of y. If and only if x equals y, so the exponents are the same. So for example, if I have 2 to the third equals 2 to the x, right, then I can notice that 2 and 2 are the exact same number. That means their exponents have to be the same as well. You're going to see in these types of equations, we typically will cross out the base once we have that they're the same, and then we get our exponents are equal, right, something like that. All right, so sometimes you can rewrite it in one step. So for example, I just need to change one side of the equation to have the base of the other. Sometimes you have to change both sides of the equation. But I'll just go through these examples and we'll handle them case by case, but you're going to see the process is pretty much the same for all of them. All right, so let's look at this first one. I have 9 equals 3 to the power of x plus 1. So what we want to try to do here is I want to have the bases, so the 9 and the 3. I want to change one or the other to have the base of the other one, right? So I want 9 to turn into a 3 or a 3 to turn into a 9, right? 9 is the bigger number, so I would change that. So in these types of problems, you want to ask yourself, is there any way that I can change 9 to have a base of 3? Can I rewrite 9 to have 3 to the power of something? And you can, right? We already know that 9 is the same as 3 to the power of 2. So then I get 3 to the power of 2 equals 3 to the power of x plus 1. And then notice that now the 3 and the 3 match. So then I can just cross these out. This just becomes 2 equals x plus 1. And then you're left with a super easy linear equation to solve. I'm just going to subtract 1 on both sides, and then I get x equals 1. All right. Now, I'm going to skip 16 for now. I'm going to go right to the next one, just because that one's pretty similar. Notice again, I have a base of 2, and then I have a base of 8, right? You want to do the exact same thing, right? I want to ask, is there anything I can do to 8 to have it, or I'm sorry, so that it has a base of 2? And there is, right? We know that 8 is 2 to the power of 3, right? And so 2 to the power of 3 equals 2 to the 2x minus 1. And so once again, same base, I'm going to cross, and then this is going to become 3 equals 2x minus 1. And then this is a linear equation. I'm just going to solve for x, right? We end up with 4 equals 2x. Divide both sides by 2, and then I get x equals 2. All right. Now, number 16 looks slightly different just because now I have a 1/2. All right. But what should catch your eye with this 1/2 is the 2. And then you also see on the other side an 8. So we can kind of do the same thing, right? I know that 8 is the same as 2 to the power of 3. Is there any way to change 1/2 so that it has a base of 2? And there is, right? I know that 2 is on the bottom and it has an exponent, an imaginary exponent of positive 1. So we can change it to not be a fraction by moving it up top and changing the exponent to be negative. So this becomes 2 to the negative 1 to the power of x, right? Any fraction we can always change by changing the sign of the exponent, all right? So then we're left with this equation, right? So that's always how you're going to handle any fraction cases, right? So then I'm going to have a negative 1 to the power of x, and the power to a powers, you're going to multiply those. So that's going to become 2 to the negative x equals 2 to the power of 3. And then once again, I'm going to cross those out. We get negative x equals 3. And then divide both sides by negative 1. And so we get x equals negative 3. All right. And yeah, that's basically the gist of this lesson, right? The next few examples are going to be exactly the same. Okay, So let's try the exact same thing with these next few examples. All right, so number 18, I have 1/3 to the negative x equals 27. Same exact idea as the one that we just did, right? I'm going to see a 3 and a 27, and the goal should be to rewrite with a common base, right? And it looks like a common base here is going to be 3. Can you write 1/3 to have a base of 3? And you can, right? That's 3 to the power of 1 on the bottom. And so to move it up top, this is going to be 3 to the negative 1 to the negative x. And this is going to equal 27 is going to be 3 to the power of 3. And so what we can do is power to a power, you're going to multiply these. And so this is going to get you 3 to the x equals 3 to the third, cross, cross, and then we get x equals 3. All right. Try the exact same thing with the next one. All right, I see a 1/3. I want to bring it to the top just by moving it. Right, it has an exponent of 1, so this is going to become 3 to the negative 1 to the power of x. And then 81, we know that that can be written as 9 times 9. And then you can split up 9 times 9 to be 3 times 3 and 3 times 3, right? So 81 is the same as 3 to the power of 4. All right, so now we have two bases of 3's. I'm not going to cross out yet, right? I want to make sure my exponents are fully simplified, right? So power to a power, I'm going to multiply. This is going to be 3 to the negative x equals 3 to the fourth. Cross, cross, and so I get negative x equals 4. Divide both sides by negative 1, and so I get x equals negative 4. All right. Try the exact same thing with the next one. I see a base of 2 right here and a base of 8 right here. And we've already done before, I can change 8 to have a base of 2. So I know this side's going to be 2 to the x plus 4, right? That's unchanged. And then 8, I know that that's going to be 2 to the power of 3 to the x minus 6, all right? And power to a power, you're going to multiply. So that 3 is going to be multiplied with the entire x minus 6. So that 3 is going to distribute to each of these, right? So then we end up with 2 to the x plus 4 equals 2 to the 3x minus 18. And then, as always, we have the same base. I can cross. So then this is going to be x plus 4 equals 3x minus 18. And then let's subtract 4 and then subtract 3x. And then so we end up with a negative 2x equals negative 22. And then let's divide both sides by a negative 2. And then we get x equals 11. All right. So hopefully you're seeing it's not so bad, right? Let's try a couple more. All right. So we have now 2 to the 3 minus x equals 8, right? Same exact process. This is just, this side stays the same. And then this one's going to be 2 to the power of 3. Cross, cross, and then we end up with 3 minus x equals 3. Subtract 3 on both sides, and then you end up with negative x equals 0, and then divide both sides by negative 1, and then we get x equals 0 as our answer. All right, try the same thing with 22. This is going to be 5 to the 2x plus 1 equals 5 to the second, right? That's 25. So cross, cross, and then we get 2x plus 1 equals 2. Subtract 1, and then we get 2x equals 1. Divide by 2, and then I get x equals 1/2. All right. Now, this next one looks a little strange. It's actually the exact same type of problem as everything else. It's only different because there's an e now. All right, I'm going to talk a little bit more about e in a second, but what you should know about e is that it's just a number. E is a number like everything else, right? So it's going to have a decimal approximation. It's going to be approximately 2.718. All right, and I'll explain more about that. It's going to make more sense in these money problems. But for now, just know that it's a number like everything else. So if I see an e here and an e here, then I can just power to a power this, and then you end up with the same kind of problem as everything else. So I get e to the 4x minus 1 equals e to the 2x. Cross these out, and then we get 4x minus 1 equals 2x. And then we can subtract 4x on both sides, and then I get negative 1 equals negative 2x. Divide both sides by negative 2, and then we get x equals 1/2. All right? And that's it for those kinds of problems. All right, the next little bit of this lesson is going to be about money problems, right, and compound interest. You're going to see a formula here, right? This formula you do need to memorize. We don't provide this to you. But basically what this is when you put money in a bank, like let's say a savings account or any other sort of account, like a retirement fund, something like that, the amount that you initially deposit is going to be denoted by this P value right here, right? So that's the amount that you're investing, right? That's the amount that you're putting in. The amount that you expect to get out of that after a certain amount of years is going to be this A value, right? So A is going to be your future value, and that's what this formula has on the left-hand side, right? Everything else, or that A value is dependent on everything else, right? The interest rate, the number of compounds, the amount of time that goes by. All right. T is the amount of years. So let's say I want to find it after a certain amount of years. That's going to go up here in that exponent. R is the interest rate as a decimal, right? A lot of times we give you the rate as a percent. So for example, if it was 5% interest, then to get that as a decimal, right? Hopefully we know how to do that. We just move the decimal point over twice, and then this gets us 0.05, all right, as a decimal, right? And then N is the number of times a year that you're compounding, right? Compounding meaning how many times you're kind of pulling interest. So for example, right, in a given year, let's just say it's a 5% interest rate. If you were to compound semi-annually, that would make N, the number of compounds, 2, right? That's how many times you're pulling interest in a year. So really, it's not like you're pulling 5% at the same time. You would really be pulling 2.5% in the middle of the year, and then maybe the other 2.5% the other year, for a total of 5% in any given year, right? So other words that you might see are quarterly. So maybe we're compounding quarterly. That would make N equal 4, right? Because there's 4 quarters in a year. Again, like let's just say it was a 5% interest. That means instead of waiting the full year to take the 5% interest extra, right, you're doing it 4 times. So 5 divided by 4, what is that, like 1.25? It's really 1.25% every quarter, right, of a year, right? You could also compound monthly, right? And that would make N equal 12, right? There's 12 months in a year, right? Just for an easy computation, let's just say I have a 12% interest rate. That would mean every month you're kind of taking a 1% interest of whatever value it is, right? And then even more than monthly, you could even go daily, right? Maybe there's a daily compound, right? That would make N 365 because there's 365 days in a year, all right? Now, the more you compound in a given year, you're going to get a little bit more money each time, right? Let's just say I invest a certain amount. If I were to invest in an account that compounds quarterly versus daily, I'm going to expect a little bit more money when it's compounded daily, right? So you would think, okay, if you just keep compounding, right, even more frequently than daily, that's going to get you a really large number for N. That's not going to mean your money's going to grow to infinity. That just means that's the fastest that it could grow with just by using compounds, right? And so that gives us this little thing up here, right? Looks a little complicated, but this LIM that you guys see right here, this is a limit. You guys would only really see that in calculus, or maybe like if you take pre-calc towards the end of pre-calc. But a limit is just as a number gets close to a certain value. So as n, the number of compounds approaches infinity. So that means as this number gets really, really large, so let's just say I keep compounding, right? Every second I'm compounding, every microsecond you're compounding, all right? You approach this number e, all right? That's where the number e comes from, and it's approximately 2.718281818, and so on and so on and so on, all right? You don't really need to know too much about where e comes from, right? I'm sure not a lot of you care too much. But what you should know is that it's a number, right? It's a number just like how pi is a number, right? You know that pi is about 3.1415, and it goes on forever and ever and ever. All right, e is a number in a similar sense of pi, right? It's just going to go on forever and ever and ever. All right, but let's actually apply this in a problem. All right, so let's just say we invest $12,000, right? I'm going to label these as I go along, right? Invest $12,000. That makes your P value 12,000, all right? And we have it at an annual rate of 3%. That means our R value as a decimal, I'm going to move that 2 decimal places over. So this is going to be 0.03, all right? And I want to find the balance after 5 years. That means your T value is 5. Compounded quarterly, right? How many quarters are there in a year? There are 4. So that means n would be 4. So I'm going to plug all of these numbers into A equals P times 1 plus R over N to the power of NT. All right? So then what I'm going to do is this is going to be 12,000. And this is something that we need to plug into a calculator, right? You're not going to be able to very easily get this number by hand. So I get 0.03 over 4, all right, over n to the power of nt. So to the power of 4 times 5, all right? Now, writing that formula down, super easy, right? The hard part is this is typically the part where kids start getting all sorts of different answers, right? And it depends on the calculator that you have. You need to be super careful with the numbers that you're plugging in, making sure that you have parentheses where they need to be. But the number that we should get for A is A to the nearest cent, right? We're always going to round these to the nearest cent, is going to be $13,934.21. All right? So that's how much we can expect after 5 years in this, with all this criteria, at a rate of 3%, compounded quarterly, investing $12,000. All right. Now let's try the same thing compounded monthly, right? So I still have the same P value, the same rate of 0.03. I still have T is 5, but this time we're compounding monthly. All right. So N is going to be 12, right? Because there's 12 months in a year. So again, plugging into this formula here, we're going to have 12,000 times 1 plus 0.03 over 12 to the power of 12 times 5. And then that's going to make A approximately, again, be careful with your calculator. Make sure that you're plugging everything in correctly. All right, let's see what this gets us. It's going to get us $13,939.40. And that's our answer here. So notice that you get $5 more, right? $5 more if you compound monthly versus quarterly. So that should kind of show you, right? The more that you compound in a given year, the more money that you can expect to get. All right. So this brings us to continuous compounds, right? Which is what I was talking about before with E, right? So let's say you invest in an account that compounds continuously, right? Then we have this little formula here. Again, you need to memorize this. We don't provide this to you. And it's still the same P, T, and R, and A that you guys have seen before. It's just now it involves the number E, all right? To get the number E on your calculator, you're going to hit second, right? There should be a second button. And then you should hit a button that says LN. All right, that's how it is on most calculators. If it's not, then you'll have to figure it out. I think there's for sure an LN button and then like a shift maybe that's going to take you to E. It should look like somewhere above it. It should look like E to the X, all right, something like that. But let's use that to solve a problem, right? So we're going to invest. We're going to have the same p-value of 12,000 at a rate of 0.03, so R is 3. Find the balance after 5 years, so T is 5, and it's compounded continuously. That means I'm going to use this formula, A equals PE to the RT. So I know that A is going to be 12,000 times E to the 0.03 times 5. All right, so again, plug this into your calculator, do that second ln, and then 0.03 times 5, and then we should get that A is to the nearest cent. Again, it's going to be 13,942.01. All right, and then you can see that that's a couple dollars more than the other two answers that we got in the other slides. All right, so that's it for this lesson, right? These are the last types of questions that you'll see in this particular lesson, right? It's only these last few problems that you'll need a calculator for. Everything else you should be able to do by hand.